going to be an extremely technical talk. This talk is more going to be just some things I found interesting in trying to sort of answer this question for myself and some of the things I found and how I'm thinking about that problem. So that's what we're going to talk about today. More specifically, I'll give you sort of on all these things kind of my perspective, which hopefully you find interesting, but some motivation and context for why is the autonomous reactors why are they being talked about, and then ultimately that comes down to sort of the economics, and so we'll do a little bit of a deep dive into what operation and maintenance costs or O&M costs mean at nuclear power plants, and then we'll sort of go on this quest together of what does introducing autonomy in that space actually mean. Okay, and then I'll just kind of wrap up. So by the end of the seminar, hopefully you'll have a better understanding of some of the economic challenges facing nuclear energy, at least as I understand them, and hopefully I have the correct understanding. Why autonomy can be a solution for that and what it means, and then my favorite thing is that engineers get really excited about things that are just really boring to normal people. So without further ado, the economics, kind of the context of nuclear power in today's, as it applies to electricity production. This is kind of what the situation is. This is how our electricity grid has been evolving with some forecasting. And this comes from, there's my pointer. Okay, it comes from the Energy Information Administration. This isn't working the way I had hoped, but it is doing okay. All right, so we can see nuclear has remained relatively constant in the past 10 years, and it's really renewables, non-hydro, solar and wind that have been growing and are continuing to grow. And part of the reason for that is solar power, the cost of installing it has come way down. I have solar panels at my house. It's lovely. I have a little app. I can see how much energy they're making. Natural gas, more or less steady. That's really going to be a consequence of the price. We can see there's been a little bit of increase. If we go back far enough, you go back to the recession of 2007, 2008. Right after that, when investment became cheap, you really saw fracking take off and cheap natural gas just come in. Okay, so that's kind of the world we're living in, which is more renewables and cheap natural gas, and I think more renewables are going to continue to be a larger and larger fraction. But it turns out, that can create problems in the electric markets if you have electric generators that aren't really flexible, and nuclear falls in that category. So in this graph, what I'm showing you is just some data from California's electric grid, where the wholesale price of electricity for part of the day goes negative. And what this means is, there's too much energy being put into the grid. This is because renewables like solar are intermittent. We can't really control when they produce power. When the sun is shining, they're producing power. And so the market is telling the generators, don't produce power, you'll make more money. There's too much right now. And so you have to be flexible to be able to respond to this. If you're nuclear and you're operating base load, you're eating this cost. And solar, they don't have a whole lot of cost. This, I guess, disconnected from the grid and just sending electricity into the ground, but there's not as big of a financial disincentive for solar to do something about that. So this is also something else that's affecting nuclear. The third thing is that operating nuclear is really expensive. So this is some other data from the Energy Information Administration, just looking at operating costs, maintenance costs, and fuel costs since 2014. And as I've got it laid out as nuclear, fossil, and gas, and you can see the operational costs. Nuclear is 2 to 5 times more than the traditional fossil counterparts. Maintenance costs were about on par with coal, but maybe 2 times as much as gas. So gas, combined cycle natural gas is just always going to win in this category. There's a huge gap there that, the nuclear has to try and catch up with. But in terms of fuel costs, nuclear wins. We have the most energy dense fuel. And that's, ultimately, this is like the advantage that nuclear will always have over every other type of electricity generation, like period. Is this. So if we're going to do something to improve the economic outlook for nuclear, we have to do something about operations and maintenance.
So just a question, where does security fit into this? Where is the security number?
I'll get to that.
But it's in there already.
So I don't exactly know how the EAI gets this information.
Okay.
As to whether or not it includes security costs, but my guess is it probably does.
Okay.
But that's right. That's a very important consideration.
Are these marginal costs, or are these variable costs, or fixed costs?
Fixed costs, I believe. It's probably both. All right. So, and the last bit of challenge is, bigger is not always better. This is from a paper by Jennifer Lovering looking at construction costs of nuclear power plants historically. The idea is, when people are doing forecasting is, okay, there's some overhead you pay on the first one, but as you start to build these things more and more, you learn how to operate them and build them more efficiently. And with nuclear, like that never happened. It got way, way worse. We call this, negative learning. Around, there's basically the blue ones are before 3 Mile Island and the red ones are after. That was a significant event in the history of nuclear power that caused some regulatory changes and construction changes and design changes and delayed a lot of projects. And that's kind of what we're seeing here. Right, and large plants are unbelievably expensive to build, right? They're still trying to finish the 2 AP1000s down in Georgia. And, they're 27 billion, they're years over behind schedule, billions over budget. But this, this is not something specific to nuclear. This is like endemic to what are called mega projects. So this is a nice book that sort of explains that and looks at some other case studies, the Denver airport, the tunnel connecting London and France. Anytime you get into a large infrastructure problem, this just seems to happen. And this book kind of argues different ways that you can sort of design the system of contracting and everything to get around that, to put the risk in the right place. But for now, this is kind of a situation that we're dealing with. So to summarize this first part, big nuclear plants are expensive to build. Big nuclear plants are also really expensive to operate and maintain, relatively. And our big nuclear plants don't really operate flexibly enough when we account for renewables. They're not incentivized to operate flexibly enough. So these are some of the challenges that is sort of going to drive, the thinking now that of what people are trying to do in terms of making nuclear more economically viable. So I'm going to give you just a little more context. And here's the capital costs. So to address those three things, right? We, the academic community, the DOE complex, are thinking about this sort of how to get at those problems. And the first one, kind of, nuclear is big nuclear is expensive to build. We're now starting to think of like, okay, we're doing that for economics of scale, right? That's the fundamental idea that's driving that design decision to go bigger. Is you're more economic, you're bigger. And that makes sense, right? So here's an example in terms of transportation, right? This is a bus in Michigan that will take students from Ann Arbor out to the airport. Huge capital costs, right? But it informs a good service and it's cheaper than any taxi or Lyft or Uber or whatever. And of course, you probably saw this here, but 4-ish years ago, scooters started showing up everywhere, right? And this is profitable because of economy of multiples. These things are very cheap to roll out. You're not really paying a lot of overhead. You don't have a driver. Your customer is doing that. And so this is, how I think the community is thinking about reactor design. If you look at advanced nuclear, everyone is starting to think smaller. Remember, O&M for nuclear is still high, right? And we haven't built these yet or rolled them out. So we can't really say for sure we know what the O&M costs are, but we should be asking ourselves, okay, we can pretty reliably believe that when we scale down like this, we scale down the size of the system, that we're gonna get savings on our capital costs. But again, what does that mean for O&M? Are we actually gonna have less operators when we build smaller reactors? Well, so to answer that question, I think we have to understand what goes into O&M costs. So our O&M costs, I'll give you some basic definitions, and Paul already kind of pointed these out. But you have fixed costs and variable costs. And the difference is fixed costs, you pay them regardless of whether or not you're producing power, right? This is like insurance, fees to the NRC, industry trade groups, staffing costs. Variable costs are things that change when, or expenses you incur when you're operating. And this is not to say fuel necessarily, but this can be, just lubricants or things in all your pump systems, whatever. Reactors have demineralizers. You have to put something in there to demineralize the water, grad waste treatment, wastewater treatment, all of that stuff. When you start to produce power, you have water flowing through the reactor, treating that water. Those types of things are kind of what you can understand as examples of variable costs. So cost estimates for different generating technologies. Blue is your fixed, orange is your variable. Your renewables don't really have variable O&M costs. We have 2 bars for nuclear here, and then your fossils on the left. So fossil relative to nuclear has a much higher fraction of variable costs. Nuclear has really high fixed costs and very low variable costs. Right. So again, when we're thinking about, okay, how to improve the economic outlook for reactors, we figured out, well, we can build them smaller, and instead of thinking about economies of scale, we can think about economies of multiples and get these things, out of the manufacturing site and to the deployment site producing energy. But the other costs, they're expensive to operate, right? Go back to, I guess I have it elsewhere, but the point is we're going to get to why this difference, right? Why is this one so small? Why is this one so big? But I guess before we get to that, estimating O&M costs, right? So this is really going down a rabbit hole. This is you think it should be kind of easy to answer or transparent. It is absolutely not. Or it may be to some people, but to me, sitting in my ivory tower, it's not. And so this is kind of just a short journey of me trying to figure this out, right? So how do we estimate O&M costs for small reactors? Well, we can start with a report that sort of does that or has information about it where we trust the authors. And we can look at where they got their data. And okay, so they got their data from another report, right? So let's go look at that report and see what it says. And this NEI report on microreactors says, all right, we are assuming that $250 to $450 per kilowatt electric is a reasonable assumption for the O&M costs. And I think in your guys' report, you said for the economics that, to work out, an optimal range would be like getting it down to 60, if I read that right. Okay, but what, I want to know how NEI got this number. And this is what they say. They say this is estimated for the first microreactor based on the following generic cost inputs, which are established based on input from several microreactor developers. Microreactor developers haven't put any microreactors to market yet, right? So I read that, and that's what I think. And I think, how much do I trust this number? Right, so these are expected to develop the range of potential conditions, including transport, accessibility, weather, climate, et cetera, et cetera. Okay, NEI is kind of an authority on this thing, and I guess lobbyist is kind of the best thing, but they're a group that is about promoting nuclear.
If I could just
Yeah, go ahead.
When we asked them how they developed it, they basically took the current values, which are about 120 to 140, and multiplied them because they didn't know an answer. And my guess is they had a private RFI, a request for information from the developers, and the developers simply provided a number with no justification.
Okay, so we're gonna dig into this. We're gonna try and we're gonna say, all right, to me, this is mostly a dead end. I feel. So, let's pick another report to start from and go down another rabbit hole and see where it takes us. So for that, under the RPC program, there is a report that came out from the Usage Catalyst in 2020. It talks about cost and performance requirements for flexible nuclear. And you look at where they got their information. Well, they got their information from a report in 2009, 2010. They don't give the exact reference. They just say this came from some INL report. But this one does a really nice job. It actually gives you the breakdown of these are the job titles of people working at the plant, and this is how much those are going to cost. And their methodology here comes back to this report from 2004, which was about advanced nuclear. And at the time, that was kind of your AP 1000, ABWR, ACR 700. And this was, by actual plant operators. So the section on overhead staffing and cost was developed by Dominion with input from Energy and TVA. That is a big chunk of your owner operators in the nuclear fleet. So to me, this is probably the most credible source. They actually are writing the paycheck for the people at the plant. Okay. But your microreactor report, right? So that's, maybe 10 megawatts electric or something. 22 megawatts thermal, something like that. Okay. This report, 600 megawatts. These are still your big nuclear 1,000 megawatts. And there's a bunch of others you can find. And you can look at the year of the study, generation of the reactor, and look at this normalized cost of dollars per kilowatt year or dollars per kilowatt electric for each year of operation. What they said at the time, and then adjust that to 2021. And surprisingly, this agrees pretty well with the NEI number, right? 305, 174, 130, 386, 284. The other thing I want to point out that was interesting about this is these two reports are about the same NGNP plan, right? So INL was going to contract General Atomics to build this thing. And they came up with very different numbers. And at the end of the report, they know this is going to be an area of future work. But to my knowledge, they never actually did that future work. But there's about a factor of, I think it might have been 2 on staffing, where INL says we need this many people, and General Atomics says we need this many people. And of course, it behooves them to say your costs are going to be cheaper, right? That's going to help the facility react. Okay, but to me, this picture is getting muddier, right? I had numbers that are, at least in the same range as what the NEI report was, different reactor technology, different time, but surprisingly consistent, right? We go from 1987 to 2009, and we're still about 300 kilowatts electric for O&M.
Just one clarification. The 99 to 386 is purely cost of living. How did I go from 100 to 386?
That should just be, inflation, or the value of the dollar at 2009 versus 2021.
Then why is the 1987 one going up by a factor of between 2 and 3, and then the one, and then that 2009 ones are going up by 4?
Yeah, that's a good question. I'll have to go back and look at the calculations that my student did for this. Yeah, because I trusted they did it well. And maybe there's a typo in there. You guys are asking the right question now, right? Anytime somebody shows you data, you want to scrutinize it.
The one thing that's very old, we found the original report. There's an Oak Ridge report in the 1970s where they have essentially the number of FTEs as a function of megawatts installed. And the curve essentially goes like this.
That we're just about to get there.
Okay, all right.
That's I believe that's this one. Okay, this is an Oak Ridge report. And these are those equations, right? So right, the number of on-site staff you need as the electrical output of your unit, and the number of units, right? So this is kind of a traditional scaling law that you see in some engineering studies. And right, in the microreactor program, so this was in a recent funding opportunity call, they were looking for or they set requirements on the design that, all right, you need to have a half, 1.5 FTEs per megawatt. They don't specify if it's electrical thermal, but I'll assume electric. What's a full-time employee? What's the average cost of that? Usually what people do in this is they just go to Bureau of Labor Statistics or the electrical utility cost group, and they just look at the number for the average electric utility worker. And that's about 100,000. Okay, so we're now at the low end for a microreactor of 50 to 150 kilowatts a year. All right, but the problem is, and in the NEI study and how they base their numbers, the Lucid Catalyst study and how they base their numbers, they're all looking at these large plants and computing some average cost per production based on that staffing. And here's something from 1987 that says something a little bit different, right? So those other reports I showed you basically say that, all right, whatever number you calculate the reactor, you just assume that's a constant in terms of your reactor output. And I think to me, it's sort of obvious that I should assume that's the case. That's probably a bad assumption. If that's only something I can make at the time, I'll make it, but it's probably not the best. And so this is a log scale. And as Mike just said, in these formulas, this curve goes like this. So do we really believe that we can build a microreactor with O&M costs in this range? Or should we believe something like Bauer's formula, right? This was developed from Generation 3 reactors in the 1980s, where everything is 1,000 megawatts electric. But anyway, we're basically two ways of getting this number, and they disagree by a lot.
Do these formulas define the range of applicability?
They might.
Because I guess they don't go down. I mean, since they're based on 1,000 megawatt reactors,
Yeah.
they probably are never intended to be used at
Yeah.
10 megawatt scale.
Yeah, right. And this is, I think of it like the LD50 problem for radiation dose. We don't have a lot of data about death rates at really, really low exposure. So we don't, my point is like, I don't think we really know what's going on here. I don't think anyone does. Yeah, so getting back to this point of kind of why this, and this comes to, again, the issue of staffing, right? So if you do enough digging, some of those reports, the Dominion report, the INO reports, they give you this kind of breakdown. They have a job title for every single value in this. And Bowers puts it at 800, so that's the 1987 number. INL, I guess 15 years ago, put it about 382. But here's the kicker, right? Natural gas, it takes around 30 to 40 people to run a natural gas plant. How is nuclear going to do that? Especially when you look at all the different categories here, right? So you say, okay, if I want to reduce my O&M costs in nuclear, what that really means is I need to take people out of the plant. How am I going to get people out of the plant? Well, autonomy. All right, so let's think about now, what does it mean to introduce autonomy into a plant? So I'm going to sort of just start with this and with an analogy of getting towards more hygienic college students, right? So we're gonna take our undergrad, we're gonna call them a structural support maintenance technician, and what this means is they're gonna pick up clutter, sweep or vacuum, and mop, keep the floors clean. Then we can take someone else, their roommate, call them a textile care specialist, and then they're responsible for making sure you have clean clothes, right? And we can automate some of these things. So you have a person with a job with assigned duties. And then you look at those assigned duties and you say, which ones can I automate? Right? Well, we have washers and dryers. We have, robots that can clean our floors or mop. But we still don't have, something automated that can pick up all of our clutter or, sort dirty laundry. If you follow robotics, this is a really hard problem that they haven't figured out yet. Right, so even if we introduce automation, we still can't fully eliminate these positions. Ultimately, this is kind of, I believe, the right way to approach introducing autonomy in nuclear power plant. We have to look at what the people in the plant are doing and figure out which tasks, just go line by line and figure out how to automate each of those things. Like, it's an incredibly boring and tedious process, but this is the exciting engineering of autonomy. So, autonomy is being talked about in a lot of places, and it's sort of being talked about in other directions from a high level. They want to say, all right, how do I just sort of come up with some general concepts to introduce levels, right? And this has been done for the Air Force. They have cool words like battle space swarm cognizance, and it's also been done for the Society of Automotive Engineers. And we see this with cars, right? Level 1, driver assistance, right? Control either steering or speed, right? We have autonomy in our cars now that keep us in our lanes, and we have cruise control. We've had that for years, and we don't have to keep our foot on the gas pedal. Partial automation, right? We can do sort of both of those things now, and Teslas are kind of at the leading edge of this, and they're somewhere in this range, but they're still not here. And so this kind of gives you, this is nice because it gives you a measured approach of how to get to the end goal, right? So you're not just taking one giant leap. But there's been, I guess, I can think of maybe two references that have sort of tried to come up with this for reactors. This was kind of my own before I discovered them, or before the other ones were published. But let's talk about that, like levels of autonomy for a reactor, what that is. So no automation, right? So Scram's actually the safety control rod Axeman. This is kind of one of our favorite stories where, Chicago Pile 1, Norman Hilberry was responsible for cutting a rope that would drop a control rod into the reactor in case things got out of it, right? So this is your safety control rod accident, right? This is what they're doing. Turns out this isn't true. If you want to know the real history of where this word came from, the NRC historian Tom Wellock has a blog post about it. But this is a funner story, so that's the one that's kind of come about. All right, so next level, operator assist, right? Reactor can supply constant power, shuts down without a fault event, with a fault or an event, requires manual startup. This is, to some degree, where we are now, right? Most of our safety systems have some degree of automation in them. Partial automation would be, you can load follow without a human intervention and build up, that's the piece that comes in, but you're still kind of starting things up manually. Conditional automation, right? You can sort of match a load and operate robustly with a fault or an event. So not something that would necessarily cause a scram, but maybe an anticipated operational occurrence or one of the lower condition events. Or high automation, right? This, it's like starting your car, right? In the 1920s, you had a hand crank, and really that old. Or today you just have a button that you push, right? And somewhere in between, we were turning a key. Okay, sorry, at full autonomy. So this is sort of modeled after the SAE one, right? 5 levels is just easier to remember than 10. So, right, so what do we automate in a reactor? Well, let's go back and look at where our people are. We've said that this is really high, operations and maintenance. And if you just look at the head count, right, these have some of the highest numbers across all the categories. But the question that Mike brought up earlier are, the challenges, security, right? Nuclear is always going to have security. I don't think we can necessarily imagine a world in the next 20 years where you have a microreactor at every truck stop without any security. I just don't see that happening. I guess that's my first one. You're welcome to disagree. But this is also a significant makeup of the people at this plant. It's my understanding that there's at least some people trying to argue with the federal government that the operator utility shouldn't be responsible for this part of the case. The government should be. Because this is like a fatality. And the other one is, your radiation protection, right? We're the only highly radioactive energy generating technology. And so we have to make sure we do that safely. We need these people. And so that's something else that just puts us at a disadvantage with coal. They may have some. I obviously don't know. Natural gas, probably not. All right, so see, these are some of the challenges. This is kind of where I would say the community is focused right now, because this is what federal government is paying us to figure out. That's a problem I think is important that we should solve. So let's look at automating operations. And the first thing to remember here is the operators in the control room are regulated, right? 10 CFR 5054 says, well, it says this, right? Depending on the number of units you have operating and the number of units you have on site, this is the number of people you can have in control room. And NewScale right now is really trying to present the case to get some change to this, because they want to have, I think, like 2 or 3 operators for 6 units. And this is just one shift per shift. Typically, planes will operate with 5 shifts. You have 3 shifts per day, 1 in training and 1 on. So about 20 people total. Using the numbers from Bowers, you can estimate the cost savings. Like the best case scenario, you don't need any people in the control room. How much money do we save? Well, we save about 10% of our total. Right, so these 4 people get replaced by computers, and that is going to, I would think, that is a very expensive proposition to figure out how to do that and meet regulatory requirements. That this payoff, it might not be there. So let's think about maintenance, and this is where I think there is more. You can build a stronger case of financial incentives around maintenance. And to get into this, I want to talk about first just a couple different approaches to conducting maintenance. And to do that, well, we're going to walk through these concepts, and I'm going to use the analogy of an automobile or a car to help convey that. But you basically have, reactive maintenance, preventive maintenance, condition-based maintenance, or sort of prognostics, health management, or predictive maintenance, right? And you go up the pyramid, it's more beneficial to your economics, your bottom line, but it's more complex. And if you're at the bottom, well, you kind of you're not trying hard enough. Okay, so this is what the dashboard looks like in my car. And our example of reactive maintenance would be, I just put electrical tape over these lights on the dash because they're bothering me. And then I'm just going to, wait for my car to stop running, and then I'll fix it. All right, so if you've been a car owner for a while, you might know that usually the first thing that's going to go is your gas. That's easy to fix, but then if you don't change the oil, you wreck your engine, and you need to buy it. This isn't really the most economic way to go about maintenance. You can have really severe failures that are really costly to fix. And if you did just a little bit of work, the problem would have been avoided. Okay, so let's look at preventative maintenance. And this is really just follow the manufacturer's maintenance schedule. It's kind of a time-based system. You don't really measure anything about your system. Look at it, you can ignore your gauges. You just say, when I've driven 6,000 miles, I replace the engine oil. That's, regardless of the condition of that engine oil. And what has happened in the aerospace, commercial airline industry, is after enough operation, those companies started to figure out that the vendors, the business model of the vendors, the engine makers, were to give you preventive maintenance schedules that helped get them more money. And so, using data from operating their airplanes, they figured out, well, we don't have to do this every 6,000. We can do it like every 7,000. And so they're able to save a little bit of money that way. Okay, condition-based maintenance. And this is, I hope, self-explanatory. But when a measurement says condition bad, you perform maintenance, right? So when your check engine oil light comes on, you replace your oil. Or when your fuel, your low fuel light comes on, you replace your fuel. Right? That's the maintenance. You wait for the signal. The last one, predictive maintenance. This is really just sort of your condition-based maintenance, or you have some condition-based monitoring, and you have a model to predict when you're going to be at the point of needing performing, right? And we have this in cars too. Most of them now have a gauge that says, all right, you can drive this far until you need to get more gas. So that's an example of predictive maintenance. You don't have that for, say, the oil, right? You can't say the condition of your oil is bad. If you get the oil leak, you have no sensor to say you're leaking a quart of oil every week. You really need to go get your car fixed. All right, so that's basically our concepts of maintenance, right? And we can choose as the owner of a piece of equipment which of those we want to do. Right. The other thing I guess I want to mention is often, at least in our review of the literature, this distinction was not made. This is kind of my distinction. I think it's an important one, but sometimes like distinguishing these two steps doesn't make sense. It's kind of the same thing. And other times, this may be impossible to formulate. Okay, so those are the different types of maintenance we can do. What is the value of that? Well, we found 2 case studies. One looking at pumps, I think at federal facilities, that showed, if they go from a reactive maintenance program to preventative, they save about 28% on maintenance. If they go from reactive all the way to predictive, they save about 50%. This was also done for wind turbines, and surprisingly, totally different technology or application, but it was about the same. And this is sort of qualitatively that value proposition of your maintenance, right? So this orange line represents sort of the service limit, right? When you have to replace the part, when you have to replace your reactor pressure vessel or whatever. And then this is how your system has been operating. And every blue dot means you took a measurement. And the gray triangles mean this is your predictive model. You're trying to predict what's going to happen. Okay, and then this is your design line, right? So above this line, your system is at a high risk of failure or should be considered failing. So if you have prognostics, then you're sort of saying, I can quantify this risk so you can operate sort of in a state of known risk. And then with prognostics and diagnostics, basically what you can do is you can extend the life of operation. So this is where you can make more money. This is where you can sort of build a safety case. Let's say that you have. Right, okay. So practically, like, how is the maintenance policy improved and automated? Okay, so this reminded me of a South Park that is probably too young for most. I'm too old for most of you. But step 1, replace the human technicians with online monitoring. Step 2, step 3, profit, right? And this is sort of where the research is, right? Figuring out what to do here. Which is, in a nutshell, I think, develop predictive models and ways of optimizing them. And this is not new. This has been around. There's a whole field about this that I'm just discovering has existed for longer than I've been alive. But here's one example of maintenance optimization. So this equation, we're going to use this as an example. This is literally a textbook example. But this is, L, the left-hand side, is your total cost for maintenance as a function of time. And, we write that as, the numerator is basically the cost of a breakdown, right? So cost of breakdown of nuclear plants $1 million a day. Then we have some probability of breakdown. And the comparative cost is cost of performing maintenance, right? So how many human hours of labor does it take to go and perform this maintenance? Right? What's the labor associated with changing the brakes on the car? With the probability of survival. And the probability of survival is just a complement of the. Okay, and our optimization problem is to just find the minimum amount. Find T that minimizes F. That's optimizing your maintenance. So there's other types of equations you could use here. This is just one I think is sufficient to understand in this context. But this is sort of how you go about doing that, right? So, the trick is, hopefully you can see is, well, I need to know what this is, right? I have a good sense of what this is. I have a pretty good sense of what this is, what my costs are. What I don't know real well is these. And then, so that's what we need to figure out. Okay, and to do that, right, our step one is collect failure and reliability data, which can be expensive, right? You're just gonna say, I'm gonna go take this pump I wanna put in my plant, I'm gonna put it in this test cell, and I'm just gonna run it to failure. And that could take weeks. Right, but if you do that, right, through operation, you can construct this type of histogram that says, okay, the number of breakdowns of this component, and then the days after the last maintenance of the breakdown. And there's sort of standard techniques of converting that to a continuous function. One that is usually used is called a Weibull distribution, or Weibull distribution. Right, so you create a probability distribution function, and from measured data, and that goes in there. And right, and so the quality of this optimization really depends on the quality of how well you can represent that function. And it turns out like this expression has a clear minimum, given its mathematical form. And so it always has one, right? And here, we can solve for it, and it's right there. I should perform my preventive maintenance every 42 days, and that will minimize my maintenance costs. All right, how am I doing on time? Good. I've never given this presentation before. Okay, so practical challenges to automation, right? We now kind of have, I hope, at a simple or high level understanding, or maybe the basic concepts of like approaches to solving these problems. Right? We can say, I can use this equation. To use it, I need to go figure these things out. Right, but the practical challenges to automation. So again, just kind of a review of sort of more context, the regulatory influence on operation. Right, this is kind of just a simple way of understanding that, because ultimately, right, with a regulator, what they're concerned about is the risk to public safety, which comes from radioactive material. Okay, so this is prevented by our cladding pressure vessel containment in our conventional reactor designs. How do we ensure that integrity? Well, there's Code of Federal Regulations, the general design criteria that is the law of the land. So our design has to satisfy this. And how do we check that that is sufficient? Well, we do some safety analysis of critical transients and accidents. And then this informs our acceptable results for a range of plant and core characteristics. And from that, I'm tired from walking back and forth. We get an acceptable range of operation. And this ultimately goes into a document that is called technical specifications. And this exists for Westinghouse pressurized water reactors. It's 2 volumes and like 4,000 pages. So it's really expensive to develop this. It requires a lot of effort. And now, you think, okay, I want to go help microreactors come to market. Like, what's my contribution as a single human engineer going to be? Well, maybe I could knock out 100 pages of this. Like, I could focus in on one thing and do it really well. And so, here's an example of technical specifications. And, so they define our quantities of interest and their acceptable limits and corrective action. Here's an example of shutdown margin. And this, let's see, can't remember what LCO stands for, but the
Limited condition of operation.
limiting condition of operation. Thank you. The shutdown margin shall be within the limits specified in the core operating limits report. So this is sort of something the utility puts together every cycle. And for different operational modes of whether like hot shutdown, hot standby, when K is less than 0, that's when this applies. If your condition is not within limits, this is what you do. You have this long to do it. But additionally, they also give you surveillance requirements, right? So this is the limit. How do you verify to your regulator that you are within that limit? You have to measure something. You have to do something. There has to be a credible explanation as to why the thing you're doing tells you that this is okay. And so here it is, right? Here's the surveillance requirements for your shutdown margin. You do this every 24 hours, right? So let's see. Right, so what does this surveillance requirement say? It's kind of like this. If you're in these modes, go refer to these other conditions. If you're in these modes, you have to do this calculation. And again, this is every 24 hours. So, you've got some poor schmuck, Francis, who goes to their shift every day, and the first thing they do is they do this. Okay, so, and this is just one example. I don't know the total number of surveillance requirements, but I would guess on the order of hundreds, with varying frequencies, right? So it could be daily, monthly, quarterly, yearly, every cycle. But if you talk about automating a reactor, what you really have to do is you have to go through all your surveillance requirements, figure out how to automate those. At least that's mine. Okay, so this is kind of the last part we're wrapping up now. This is a project that I have with Professor Lindley, which is sort of why I was invited. This is sort of the thing we're trying to figure out. And it's also in collaboration with University of Tennessee. And here's just kind of one slide overview about the project. But what we're trying to do, right, is expand this idea of how do I operate my reactor, taking into consideration the health of the components in a way that will do that that we can call optimal, right? But I'm not giving you an equation and telling you it's optimal in this sense. But part of the reason for doing this, right, is they have one crane to reload 6 reactors. And that basically means they're reloading a reactor every 2 months. If something happens where those 6 reactors kind of get out of schedule, they can only reload one at a time. Right, so, what are we doing? Well, Una is running high fidelity gear models, and she's looking at, the wear and tear if we do load follow, using control rods, or, the other system they have is just dump the steam going to the turbines into the condenser. And so in that case, you keep the thermal power constant, which is going to increase the fluence on your vessel, right? So, we have this choice. We want to be able to develop a methodology to quantitatively make this decision, which is, okay, I'm being told to go down in power. How should I do that? Should I insert my control rods, or should I just bypass the turbine? Additionally, this is where what I'm working on here is figuring out, how can we have a reactor? So this is, if you can recall, going back to the level of automation, and it was step level 2, have the reactor basically be able to load follow without really direct operator interaction. How do we control rods? How do we have a model that can predict the future state of our reactor that is accurate? And it's going to help it match the target power better. Right, so that brings us to the and to summarize, current commercial power, I think, is the challenges it faces that it's too expensive to build, to operate, and in this base load mode, it's too inflexible to operate markets with renewables. But I should point out that even our existing fleet has to meet utility requirements documents that specify what it should be able to do in terms of flexible power operation. In the US, there isn't really a whole lot of, well, not really many of our reactors, save for maybe a couple, do flexible power operation, but they do this in other countries. France does it, Germany has done it. But advanced reactors trying to solve these issues by scaling down a reactor size and automating operations and maintenance. And my point is, like, there are really big and significant challenges to this, and understanding the problem and the solution is somewhat important. Some questions? Yeah.
I just had a question on the economics. So if you are moving to automation, so you're adding loads of extra systems to your plant, how does that shift where the jobs go? So are you going to have more expensive engineers that need to do those jobs instead of the plant operators. And therefore, how significant is that trade-off in cost, right?
Yeah. Yeah, that's a great question, and I don't think I can give an intelligent answer to that, but I think that's exactly a question that someone should be thinking. You know, I think as I've seen like news articles that say like, oh, this company or, you know, this place is closing this coal plant and replacing it with natural gas, so that they're losing 500 jobs. But I think, you know, because the staffing levels at nuclear and coal are similar, you know, you see things like what TerraPower is doing in, I think it's Wyoming, where they're gonna put they want to put a reactor at a former coal power site, which is, I think, a very good idea. Ben?
So could you had on slide 38, which I appreciate is a whole load of slides ago.
Type 38, enter.
Really?
Is this PowerPoint?
Yeah. Oh, cool.
That was really good. So when you've got like the 335 on automation there, how would you see automation interacting with fault condition safety claims? Would you see it being that your automation system would have safety claims associated with it, or would you have a reactor that could cope with whatever the automation system threw at it, but you would then use automation for investment protection, maybe, and certainly operation?
Yeah. So, yeah, I think let me try and unpack that question a little bit and then give an example. So in the sense of a safety system, this you can see that we kind of already have in our reactors. My opinion is that this should never override your safety systems. But this example of like, okay, operation in a fault or event, I think a good example there would be like a stuck rod. Right? I worked in a fuels group that they got a call from the plant when they were going through startup, and they said, this control rod is stuck. Can we still operate the cycle? And they had to do that calculation. So that's kind of the, you know, if at some point, well, another one in BWRs, right? If you get a bundle that starts leaking, you'll insert a rod to reduce the power located that region. So I would say that is kind of the adapt operation to a fault. That's kind of the intent of it.
Right. Okay. Rather than perform a safety-related function.
Yes.
Thanks.
Other than a scram, right? Scram is at the top of it, so presumably you're gonna.
Well, yeah, you can automate that, but in terms of when those things come into competition, right? Operating to maintain some economics or something versus shutting down safely.
So there's that 2 seconds. Well, this is
Scram system will be a lot less sophisticated than some of the automation systems.
Yeah.
So
no, it's
is this the dominant issue for a new plant or a dominant issue for an operating plant? I can see for an operating plant where you're going, but for a new plant, it's the capital cost. Because even with insanely high operation and maintenance, that's only about 10 or 15% of the total cost. Once I have to amortize everything else.
Yeah. Right. So I think autonomy, like this, especially for maintenance, is sort of more important to the existing fleet.
Okay, that's what I was thinking.
Yeah,
You were going-
those plants, you know, 60, 80-year-olds, you paid off your capital costs. You should be making money hand over fist. And if you're not, like, why? But yeah, new reactors. Yeah, I think there's just this idea that
and we just, I just wanted
expanding
to provide
nuclear
our
energy
baseline, 'cause
through
I
smaller
learned
modular reactors or micro reactors, you know, they want those to be autonomous. And I guess that's also in part following from what came first, which was the Department of Defense's village. DOE is kind of trying to ride the coattails there, I think.
But when you say the way you follow through your logic about the car analogy,
Yeah,
automobile analogy, autonomy was essentially autonomy during operation, but there are still people on site doing it. Many times when I see autonomy for the advanced reactors, it's essentially I just leave them alone and they do their thing. that's a whole different level of autonomy, which would lead me to worry about some other things, which is how do I control them at a distance? But that isn't what you're after here.
No.
Okay.
I think the other thing that I like to point out historically is I'm probably paraphrasing, I don't know the exact quote, but when the Navy was developing light water reactor technology, I believe Admiral Rickover says, like, you can't make these things complex to operate. These are going to be operated by 18-year-olds, right? These aren't your best and brightest out there, controlling the reactors. They have to be kind of idiot proof. Yeah, so I think that's as much as you are into sort of designing reactor systems, that's how I like to think about it. Like, how can this thing be just idiot proof?
And I guess it follows on from that. If you are adding automation to the plan and you're adding these extra systems, you're going to raise the capital cost. I don't know how significantly, but if you raise that capital cost, is it still worth doing it? Is it going to offset those operation maintenance, or will it only offset those operations and maintenance, I guess, 30 years into the plant's operating lifetime?
Yeah, that's another question I think would be considered in development of those systems. So I think there's a couple ways to think about it. The nature of the autonomous system. I also want to point out, like, some people like to be pedantic about automation, autonomy, and those words and what they mean. I kind of just use them willy-nilly. But I think you can conceive of designs in your system that don't require like sort of adding something after the fact. And this has been done before. So there's some work, maybe I'm doing some of it now in a different project, but it's not a new idea. There's some work on it from 18 years ago, where they developed what they called this, I think it was automated reactivity control, which is basically kind of a device you could put on an SFR fuel bundle. It was temperature controlled, where they had a liquid absorbing material at the bottom, and so when it came too hot, that would expand up and shut down the reaction. So in terms of autonomy, right, I think you can get creative and think about using physics to give you that autonomy rather than these engineered systems.
So I think another, maybe it's a second order feedback that's important to consider at the economy scale is that reduced staffing levels might get people over the hump of wanting to order. I mean, there's a complexity in maintaining a staff.
Yeah.
Right. And so reduced staffing levels could allow larger order sheets, create opportunity for more learning by doing, because you're building more reactors, right? And so I don't have any research to back it up, but I feel like if we look at microreactors, where you probably are going to want to have hundreds of them deployed to get the right kind of economy of multiples.
Yeah.
You're going to need to be able to market them in places where you can't market at staffing levels that are too high.
Right.
So it's going to be sort of a market necessity.
Thanks, Brendan.
Yeah.